So you can sort of take that two ways. It might mean that for each year when I make a chip, after it doubles, well, now I can make that same chip, but I get twice as many transistors, so in some sense it's more powerful. Or you can think of it as just that the transistors are just getting cheaper and cheaper. Now, Moore's law is not some law of nature like the law of gravity. It's just an observation about how transistor manufacturing tends to go, but it's been true for over 20 years, and it seems to be continuing to be true. So Moore's law is why you can have computers now that are getting cheaper, and they're showing up in thermostat and microwaves. Essentially, it's the doubling quality of Moore's law, making what used to be a computer that would fill a room and cost millions of dollars now is like the size of a sugar cube and costs under $1. That is the effect of Moore's law, where you think of doubling, well, just one doubling, it's not that big. If you have 10 doublings, that's a factor of 1,000. So that's how you get from the room down to the sugar cube. The other way you can think about this just in your own life is imagine buying, maybe 6 years ago, buying a $50 MP3 player, and it had some amount of capacity. Maybe it had 1 gigabyte of capacity. And then a few years later, with the same $50, if you bought an MP3 player, it might have 2 or maybe 4 gigabytes of capacity. And then a few years later, for the same $50, well, now they all have 8 gigabytes. And what's going on is, well, basically there's a chip in the MP3 player that does the storage, and by Moore's law, the manufacturing of that chip, because there's more transistors that fit in there, they can just offer, for pretty much the same price, they can offer more and more capacity. So that is the exponential quality of Moore's law. So to talk about computers, I'm going to talk about the major parts that go into one. Largely, here's a little picture of a computer. I'm going to say that there's the CPU, which is sort of the brains of the thing. And then there's RAM, which is sort of the temporary scratchpad memory. And finally, a disk or flash for persistent storage. So we'll talk about each one of those parts. So probably the most important part of the computer is the CPU. It stands for Central Processing Unit. And it's inevitably described as kind of the brains of the computer. It actually does the computing. So the CPU has certain fairly simple operations that it can perform. And so when you say that a computer runs at 2 billion operations per second, really that's talking about the CPU. That means the CPU can do 2 billion things per second, and that's a very typical number for 2012. To say that it's the brains, we have to think about, well, the run button in the earlier coding exercises where you had the code and then something was executing the code. Really, that was the CPU that was taking in that code and doing it. Before I talk about RAM and disk and those things, I need to brief word about bytes. So a byte is the sort of most common measure of information storage. So 1 byte refers to approximately 1 letter that you might type, like a T or an X or something, that fits in 1 byte. And later on, I'm going to talk about RAM and disk and things like that. And those are all the sizes, how much information can they hold, those are all measured in bytes. And later on, I'll go into more detail about the different sizes that you might have. For now, I'll just say that 1 megabyte is a common size. That's about 1 million bytes. And 1 gigabyte is about 1 billion bytes. So with that in mind, let's go to our second bit of technology here. So RAM, stands for Random Access Memory, or we might just say memory. And RAM is the temporary storage used by the CPU to hold data and code that it's using right then, just in the course of doing computation. So in the code, when we said something like new simple image flowers.jpg, and I would say, well, this kind of loads the data into the computer, really what was happening is the bytes of that data were being loaded into RAM. And then once they were in RAM, then the CPU could do operations on them. So when you wrote code like pixel.setRed0, really that was going into RAM and manipulating the data, actually making a change. So all that sort of active stuff happens in RAM. The main thing about RAM is that it is not persistent. And what that means is when the power is removed, it just goes blank. So it just works well as fast temporary storage, but it's not long-term storage. And you can I think you can have some intuition about that if you think about you're working on some, a paper and you're typing in a word processor, and then suddenly your computer shuts down. Maybe it crashes or the power goes out or something. And so you have a sense that, well, whatever you were just, those last few bits you were typing, those are gone. Those were just in RAM. and the version that you have is the version that you saved. So in a word processor, when you hit the save command, really what you're doing is you're taking the version that it's in RAM, this kind of temporary version, and you're writing it to disk. And so, and disk is something we'll talk about in a second. So that kind of gives you the sense of, well, what does it mean to be persistent like disk or volatile like RAM? All right, so that leads us to our third hardware component, persistent storage. So the main thing about persistent storage, it's a big area of bytes, but when you remove the power, the data stays there. So for the longest time, persistent storage in computer has been done with with a hard drive. So a hard drive has a spinning disk in it, and there's a little head that writes magnetic patterns on the disk and does that to record zeros and ones and store data. And so if you have a computer and you hear kind of a high-pitched whining sound, what you're probably hearing is the hard drive disk spinning in its little enclosure. More recently, there's been advances in what's called a flash drive. And so a flash drive also stores zeros and ones persistently, but it's solid state. It just uses a chip, a so-called flash chip. So there's no moving parts. It's very small. It's very reliable. So flash chips are what's used to make those little USB thumb drives or an SD card that you might put into a camera or something like that. It used to be that per byte, flash was much more expensive than hard drives, and so hard drives were used for anything. Sort of following the pattern of Moore's law, flash chips have been getting cheaper and cheaper, and so it may be that the hard drive kind of dies out for day-to-day usage. Like we don't need it, we can just use these chips. So it remains to be seen. So when you've got a hard drive or a flash chip that just has this big area of bytes to do persistent storage, just on its own, it's not really ready for the user to use. Usually what happens is the hard drive or the flash drive is organized as what's called a file system. And so the file system is just a way of organizing this big area of bytes and giving it that sort of familiar structure of files and folders, and they each have names and you can move them around and stuff. And so a file is really just a way of taking some area of 100,000 bytes and assigning a name to them, saying, well, look, this is flowers.jpg. Flowers.jpg, that name refers to these 100,000 bytes, and then the user can copy it or move it around or whatever. So the file system just facilitates for you seeing what data you have on there and moving it around and organizing it. So that's our quick introduction. So actually what I'd like to do is show you just pictures of actual hardware. So this is a picture of a motherboard. So this is a computer, a shuttle computer I bought in, I think, 2008, and then it broke. So it became my little demo computer. So this is a cheap computer, about $200 with all the parts. So this is the motherboard, all the electronic components plug into. And right here in the middle is maybe the most important component. That's the CPU. So we'll zoom in on that. So if you kind of zoom in and look at the CPU. So this metal package has the CPU chip in it. And I'm going to flip it over. If you flip it over, you see there's all these gold pads here. So the CPU is the most complicated chip on here, and so it has a very large number of connections, electrical connections to the motherboard. And so then I can look again at my Wikimedia image, and now you can appreciate, well, so there's these little tiny wires around the outside. So these connect to pads on the package, the gold pads we were seeing, and then inside the package, they connect to little tiny spots around the chip in order to get the electricity into the transistors on side of here. The other thing I'll point out here is this copper thing. There's a second chip underneath here. This is called a heat sink. And so the chip, because it has electricity running through it, it can heat up. And so there needs to be a way of dissipating that heat. And so this is made of copper. Copper is really good at conducting heat. And so by just sort of bolting that on there, it keeps the chip cool enough to operate. There used to be a heat sink on top of the CPU here, but I removed it just so I could take it apart and show the CPU. Alrighty. So that's the CPU in this computer. So now let's look at the RAM. So if we look at the side of the computer here, this is the RAM. It's on a little separate card. And in this picture, I've removed the card. So the card fits into this slot here. So that's RAM. So that's about, that's 512 megabytes of RAM. This is some years ago. You probably couldn't buy a RAM card that small nowadays. So you can see there's 2 chips here, and then there's 2 more chips underneath the stickers. So this was made with 4 chips. probably by Moore's law, when this card was manufactured a few years before, it probably used to be 8 chips. And then by Moore's law, they can fit more onto each chip, and so they could just save money. So for the same 512 megabytes, they could use fewer chips, so it's cheaper. So that's what we have, CPU and RAM. So the last thing we need is persistent storage. So for this computer, persistent storage was provided by this. This is a hard drive. So this is a 3.5-inch hard drive, very typical size for a desktop computer. So this is where there's the spinning magnetic disk in here. And this connects to the motherboard by this little SATA cable, which is a standard thing. So those are the 3 parts of a computer. That was a $200 computer, and it sort of did everything you'd want a computer to do. More recently, now we've got this alternative to the hard drive. So this is a USB flash drive, or sometimes called a thumb drive. So it's tiny, and I took this one apart. And so if you look inside of it, this is a flash chip. So this is the chip that just stores persistent data, little zeros and ones, as little groups of electrons. So this is the thing that's competing with the hard drive. So this is a 1 gigabit chip, so it stores 1 billion bits. And later on, we'll look at how many bytes that might be. So that's a thumb drive. This is an SD card, which is just similar, just an alternative to the thumb drive. It's really it's the same technology. It's just a different shape, basically. So this is the sort of thing you would use inside of a camera. So as a last example, looking at that big computer, so one of the effects of Moore's law is that you get these cheap little computers that can sort of fit into different places. So a little computer on a chip is known as a microcontroller. And the idea is that instead of having all these separate chips, you can fit the CPU, the RAM, and the persistent storage all onto one chip. And it's not going to have a lot of power, but it's going to be cheap. And Moore's law has made that possible. So microcontrollers now, you can buy essentially the whole computer for under $1, and it's just on the one chip. So these are the kind of computers, or I should say microcontroller, that you would find in a thermostat, or they're probably scattered around your car doing little computer functions. So a neat example of a microcontroller is this guy. This is an Arduino board. And this is a free and open source board used by artists or hobbyists, or just for kind of playing around. So this is the chip. This is the microcontroller. So it has a little bit of RAM, a little bit of CPU, and a little bit of persistent storage, just all on there. And then it's put on this board with some other support chips. So this is a USB chip, and it's got some power chips here to just make the whole thing work. So you can buy a version of this, I think, for about $20. And the idea is it's just a little computer, a chip. And here's a picture of a chip that I'm linking to from Wikimedia. And so a chip is made of a little fingernail-sized piece of silicon. And then different electronic components can be etched onto the silicon. And this allows you essentially to make the components very, very cheaply. So the most common component put on here is transistors, and you can make all sorts of stuff out of transistors. So the things I'm going to talk about later, CPUs and memory and whatnot, those all come down to chips that look like this. Now, a chip like this is said to be solid state, meaning there's no moving parts, there's no gears, there's no wheels. In a way, that makes it very reliable. And as I said before, they can be made pretty cheaply. And so this is one of the driving forces in the computer revolution. I should point out, this is the element silicon, which is like glass, not to be confused with silicone, which is like that kind of soft, rubbery stuff. So one of the most important forces driving silicon development is this thing called Moore's law. So this was formulated by Gordon Moore, and it's just an observation about how the manufacturing of chips with transistors on them tends to go. And what the law says is that